A bridge doesn't collapse because someone made one careless mistake. It collapses because a series of decisions, each one reasonable in isolation, converge at exactly the wrong moment. And sometimes, the moment that destroys a structure is the very moment designed to prove it was safe. That is the central paradox of engineering validation. You build something, you test it, and in testing it, you find out whether your assumptions were right or catastrophically wrong. The question this episode asks is a simple one. How does a structure survive years of design, review, and construction, only to fail during the controlled test meant to certify it? To understand that, you need to understand what an engineering validation test actually is. At its core, it is a formal process of applying known, measurable stress to a structure or system to confirm that it performs according to its design specifications. The distinction engineers draw is between verification, does this design meet the written requirements? And validation, does the finished structure actually do what users need it to do under real conditions? Those two things sound similar. They are not. A design can verify perfectly on paper and still fail validation in the physical world. The gap between them is where disasters live. In the case of a bridge, validation testing typically means applying load, weight, force, dynamic stress, in a controlled and graduated way. Engineers monitor deflection, strain, and structural response at each stage. The expectation is that the bridge will behave predictably, that its response to load will match the mathematical models built during design. Early stages of such tests almost always go well. Instruments confirm what the models predicted. Confidence builds. The team moves to the next load increment. And that growing confidence is itself a warning sign that is easy to miss. When early results match predictions closely, there is a natural human tendency to trust the model more than the structure. The model becomes the reality, and the physical object becomes merely a confirmation of it. Anomalies get explained away. A slightly unexpected strain reading gets attributed to instrument placement. A minor deflection outside the predicted range gets absorbed into the margin of error. Each individual judgment is defensible. Collectively, they can be fatal. This is not a failure of intelligence. It is a failure of the organizational conditions around intelligence. When a test is expensive, when a project is behind schedule, when careers and reputations are invested in a successful outcome, the threshold for calling a halt rises. The same data point that would trigger immediate concern in a neutral observer gets filtered through layers of institutional pressure before it reaches a decision maker. The failure event itself, when it comes, is rarely a single dramatic rupture from a standing start. More commonly, it is a cascade. A connection yields slightly beyond its design limit. That transfers load to an adjacent member. That member was already carrying more than the model predicted, because the first anomaly had been redistributing stress for some time. The cascade accelerates faster than any human observer can track, and what was a controlled test becomes an uncontrolled collapse. The physical sequence happens in seconds. The organizational sequence that made it possible took months or years. Wine. Investigations into bridge failures during testing consistently identify layered root causes. At the technical level, there is almost always a gap between the idealized model and the real structure. A weld that introduced residual stress, a material that behaved differently under dynamic load than under static load, a connection detail that was designed for one failure mode and encountered another. These are not signs of incompetence. They are signs of the irreducible complexity of physical systems. At the organizational level, investigators typically find that warning signs existed and were documented, but that the documentation did not reach the people with authority to act on it, or reached them too late, or was framed in language that obscured its urgency. The gap between the engineer who noticed something and the decision-maker who could have stopped the test is often surprisingly wide. At the ethical level, the harder question is about the design of the testing process itself. A validation test is supposed to be the moment of honest reckoning, the point at which the structure either proves itself or reveals its limits in a controlled environment. When institutional pressure compresses the graduated stages of that test, or when the criteria for halting are defined loosely enough to allow continued loading past early warning signs, the test is no longer fully honest. It has become a performance of validation rather than a genuine search for failure modes. That distinction matters enormously because the purpose of finding failure during a test is precisely to prevent failure in service. A bridge that fails during testing, with no one on it, in a controlled environment with investigators present, is a success of the safety system, even though it is a failure of the structure. A bridge that passes a compromised test and then fails in service is a failure of the safety system in the most consequential possible way. What changes after a testing failure, when the investigation is thorough and the findings are acted upon, is the design of the testing process itself. Load increments become smaller, halt criteria become more explicit and less subject to on-site interpretation. The authority to stop a test gets pushed down to the engineers closest to the instruments, rather than reserved for project managers with schedule pressures. Independent observers with no stake in the outcome get added to the process. Structural monitoring technology has also changed what is possible. Sensor networks can now track hundreds of data points simultaneously and flag deviations from predicted behavior in real time, faster than any human observer. That does not eliminate the organizational problem. Someone still has to act on the alert, but it removes the ambiguity that allowed anomalies to be explained away. The deeper lesson, though, is not technological. It is about the relationship between models and reality. Every engineering model is a simplification. It captures the behavior of an idealized structure under idealized conditions. The physical structure is never the model. It has manufacturing variations, assembly tolerances, residual stresses, and material properties that scatter around the design values. The test is the moment when the model meets reality, and the honest purpose of that meeting is to find out where they diverge. When that purpose gets subordinated to the goal of confirming what the model already predicts, the test loses its value. It becomes a ritual rather than an investigation. Engineering, at its best, is a discipline that takes failure seriously, not as an embarrassment to be avoided, but as information to be sought. The structures we trust most are the ones whose designers asked hardest how they might fail, and built the answers into the design. The testing failures that changed practice did so not by discrediting engineering, but by forcing it to be more honest about the gap between what we calculate and what we build. That gap never fully closes. It only gets better understood. And the next time you cross a bridge, the reason it holds is partly because somewhere, at some point, another one didn't, and someone paid close enough attention to understand why. This content is for educational purposes only. Do not attempt to recreate any described experiment or procedure.